Good day, everybody. We're combining this simple notion of the greatest common divisor of two integers with the summation notation. Now, just to get a feel for what this means, the first two, let's do the first two, let's say, would equal to the GCD, and I'm going to leave out the GCD part. It's commonly dropped. The GCD of 1 in 221, which is, of course, 1, plus the GCD of 2 in 221. Okay, add it 98 more times, right? Now these first two are just 1 plus 1. Now you might ask, well, when is this actually going to have a GCD that's not equal to 1? Well, the very first time would be if you take a look at 221 and its prime factorization. It's equal to 13 times 7. So 13 times 17, excuse me. So the very first time, and let me come down here a little bit further, plus 13 would appear, right? The very first multiple and the smallest multiple of 221. Now notice that since this is the prime factorization, the GCD will be 13 here. And this simple prime factorization makes this problem quite simple. So see, most of them are going to be ones, okay? Then we'll run into 17 in a little bit. That'll add up to 13. I mean, that'll be 17 when you take the GCD. So let's continue here and see how this is going to go. Again, I just repeated what I wrote down up here. Now, this should be clear since 13 and 17 are the only divisors of 221, and they're prime divisors. The GCD of an integer in 221 has to be equal to 1 unless we have a multiple of 13 or 17, okay? And so that, and it has to be less than 100 also, of course. But anyway, so let's move along. So it's important to count the number of multiples of 13 and the number of multiples of 17. Okay, we see one of them up here, but this floor notation is kind of nice. It just chops off any fractional part. If you divide 13 into 100, you get 9 left over. You get 7 with 9 left over. So the floor function just chops that off. So there's 7 multiples. Now, you don't really need the floor function to know that, okay? And then right here in a similar fashion, this would be 5, okay? So what this says is that there's 5 multiples of 17 less than or equal to 100, and there are 7 multiples of 13 less than or equal to 100. Okay, so this becomes a fairly simple task. Here's our original problem. So we can write down the 7 multiples of 13, but that is going to be a GCD of 13, right, also. So you'll have 7 times 13 right here. And this literally would be, 13, 26, 39, 52, and so on. But there's 7 of them, but each time you hit them, that's going to add that's going to add 13 to the GCD. Okay, the GCD will be 13. Okay, so in a similar fashion, you have 5 times 17 right here. Okay, now we've used up 12, right? So that means there's 88 left over that are going to be relatively prime. So we can put plus 12 right here. So this is equal to plus 12. So it's 7 times 13 plus 5 times 17 plus 12 is our answer. And that resolves to, I believe, 91 and 85, 176. Oh, this should be 88. I'm sorry, folks. I said that backwards. 12 of them get eliminated. So let's fix that problem. Okay. Okay, that should be 88, folks. Again, there's 88 left. We used up 12 of the numbers between 1 and 100 because they were either a multiple of 13 or a multiple of 17. So there's 88 left. And so if you add these up, you get 91 plus 85 is what 176, and 176 and 88 is 264 is what I'm getting. 264. So there's a nice little computation. I think this is like a low-level competition problem. The Math Bonanza, I think I've seen this at the Math Bonanza. That's in California somewhere. But in any event, this is a nice little problem based on the prime factorization. Notice I chose a pretty easy constant. If you had a lot of multiples, if you had some exponential powers of primes in here, you would have to account for a lot more multiples. Okay, so I made it simple by using what they call a semi-prime right here. But anyway, that does it, folks. 264 is the answer. Let's write it up here with the monster's approval. The hybrid plant animal Venus flytrap, right?